Let's compare the quantum Fourier transform to its classical analog. And then let's see how the quantum Fourier transform is used to perform phase estimation. Phase estimation is an important part of the order-finding subroutine of Shor's factoring algorithm. Phase estimation is also used in many other quantum algorithms. It is a practical application of the quantum Fourier transform. In the previous few videos, we have seen examples of the quantum Fourier transform for a single qubit, for 2 qubits, and for 3 qubits. We saw matrix representations, and we also saw quantum circuit diagrams. This quantum circuit diagram is for the general case. We have n qubits over here. So each of these horizontal lines, they represent a qubit. And we have some little dots, and they tell us that there are some parts of this picture that are missing. So you have to fill them in, and the number of qubits that you would use to fill in depends on how big n is. So in this diagram, I'm showing the first qubit and the last qubit, as well as the second qubit and the second last qubit. So what does this quantum circuit diagram actually tell us? It tells us that we begin with a computational basis state, and then we apply a sequence of unitary gates, and at the very end, we're left with a result. And that result is a transformation from the computational basis to the Fourier basis. So at the end over here, we have performed the quantum Fourier transform. Let's examine the parts of this quantum circuit diagram. We have this H over here, that is a depiction of the Hadamard gate. And then we have all of these R's over here. They are conditional rotation gates. So R2 all the way up to Rn. And n over here, that is the same n that specifies the number of qubits in our register. So we first initialize the qubits in this register. They have to have an initial state. So we have a string of zeros and ones that we can encode into the states of these qubits. And then we apply a Hadamard gate followed by this sequence of controlled rotations. And this circle over here, and this circle here and here, that tells us that this qubit is acting as the control. And this over here, this is the target. So we have a sequence of n-1 controlled rotations. So we have n-1 controlled rotations plus this Hadamard gate. That gives us a total of n gates in this part over here. So we're applying n gates to the first qubit. What about the second qubit? In total over here, if we include the Hadamard, we have n-1 gates. And we're counting this controlled rotation as 1 gate. So it has a controlled qubit and a target qubit. And those 2 qubits are involved in implementing this gate. And now, what if we skip all of these intermediate qubits that are somewhere here in the middle? And if we go all the way to the second last qubit, we have 2 gates. So this is 2. And then finally, we have 1 gate over here. So all of this part gives us the correct phase factors. So we produce the correct phase factors for the quantum Fourier transform. But the order in which these qubits are is actually incorrect. We have to reverse the order by implementing swap gates. So we have to swap the first and the last, the second and the second last, and so on. And if n is actually odd, then there's going to be a middle qubit. We're going to have 1 qubit in the middle that is not paired, or you can think of it as being paired with itself. So we don't have to swap that middle qubit. I'll give you an example. So consider the case if we have 4 qubits over here. So if we ignore those little dotted lines, so if we have 4 qubits, we have to implement a swap gate that swaps qubit 1 and qubit 4. And then we also have to swap 2 and 3. But then that's it. We don't have to swap anything else. If we then introduce a qubit in the middle, if we have a 5th qubit, that would correspond to n equals 5, well, then we don't have to add any extra swap gates, because this qubit in the middle does not need to be swapped. So at most, we will have n on 2. We'll have half of the number of bits. That's how many swap gates we will need. But we won't always need n on 2. So we can actually take the floor of this. So for that example of 5, we don't actually need 2.5 swap gates, right? We're not going to implement half of a gate. We just need 2 gates. So this is always going to be an integer number. We need an integer number of gates. It's a positive integer. So for 5, if you put 5 in here, you're going to have 5 on 2, which is 2.5, and then you take the floor, and that gives you 2. So this grows linearly over here. Now let's take the sum of all of these gates over here. So what is that going to give us? We have n plus n minus 1. So that's the first and the second qubit. And then we're going to have all of the intermediate qubits. And then finally, the second last and the last one. So that's going to be 2 plus 1. Well, this is an arithmetic progression. And we can group this term and this term together, and this term and this term. And all of those mini sums are going to give us n plus 1. And how many copies of n plus 1 are we going to have? Well, there's going to be half of n. So that's n on 2 times n plus 1. So this is the sum of this sequence. And what can we do then? Well, we can actually expand this out. That's going to give us 1/2 of n squared plus 1/2 of n. So this is actually a quadratic equation. You can see if we distribute this n inside over here. So this term is quadratic and this term is linear. And this is very important. The quadratic term will dominate the linear term in the asymptotic limit. So if we consider the asymptotic limit of n being really, really large, this is going to contribute much more than this term. And this term over here, this is also linear. This is bounded by a linear function. So that means in the asymptotic limit, it's not going to be very significant compared to this quadratic term. So the only thing that will differ from this expression is actually a constant factor at the front. Because each of these swap gates can actually be implemented using 3 controlled NOT gates. So have a look at this diagram in this green box. These two symbols are different symbols for the swap gate. So they both represent this operation of swapping the states of 2 qubits. And we can implement these using these identities. So these are circuit identities. We have the controlled NOT gate. And this dark circle over here, that tells us that that's the controlled qubit. And this target over here, that tells us that's the target qubit. And if you implement these 3 successive controlled NOT gates, either in this combination or in this swapped over combination, you're going to have something that is equivalent to the action of the swap gate. So if we want to count each of these as an individual gate, when we're implementing each of these swap gates, we can add an extra coefficient of 3 over here. But it's still going to be bounded by a linear function. So we're going to have a linear contribution that depends on n, and then we're going to have a quadratic contribution over here. So what can we conclude from that? Well, we can conclude that the quantum Fourier transform, or the QFT, so the quantum Fourier transform is going to grow in the asymptotic case as little n squared. It's a quadratic dependence. So we ignore all of the linear contributions because they are not significant in the asymptotic limit. And let's actually write this in another format. We can write this as the log base 2 of big N, where big N is the dimension of the Hilbert space. So big N is actually 2 to the power of little n. And we can write this squared over here. So this is another way to represent that growth in the asymptotic limit. And we can also use big O notation for this. And we will introduce big O notation when we compare some quantum algorithms in later videos. So that is the quantum Fourier transform. Let's compare the quantum Fourier transform to the fast Fourier transform. So the fast Fourier transform, or FFT, this one grows as 2 to the power of little n times n. And we can also write that as big N So this 2 to the power of little n, that's the same as big N, the dimension of the Hilbert space. And then this little n is the same thing that we have over here. We're dealing with log base 2 of big N. So we have a linear function times a logarithmic function, n log n. That is how the fast Fourier transform grows. And you can also put this in big O notation. And what about the discrete Fourier transform? If we just take the definition of the discrete Fourier transform, so dft, well, that's going to grow as the square of 2 to the n. So we have 2 to the 2n. So the reason this 2 is here is because we're squaring it. And that's the same as big N squared. So this grows a lot faster. And that means it's going to take a lot more time to execute the algorithm. When we're counting these gates, what we're doing is trying to estimate how long it's going to take to execute this algorithm. And if the number of gates grows quadratically, it's going to take longer to execute that than if it grows linearly. And we're considering the asymptotic limit when n is really large, because that allows us to compare algorithms. We want to see how do they compare in these limiting cases for really large values. So there is an advantage of performing the fast Fourier transform on a classical computer. So this is going to be an advantage compared to the discrete Fourier transform. So when I say discrete Fourier transform, I mean if we just consider the definition of the discrete Fourier transform and we just evaluate all of those terms, that's going to grow with big N squared. So this big N is the dimension of the Hilbert space, and it's going to grow quadratically with that value. And you can see that there is an exponential saving. Instead of having this quadratic growth over here, we have n log n. And we lose one of these exponential factors. And it turns into a linear factor over here. So it depends whether you're thinking in terms of little n or big N. And you can see there's another advantage over here for using the quantum Fourier transform. So it's another exponential factor. But it's actually not as simple as just using the quantum Fourier transform. We want to use the quantum Fourier transform as a part of a bigger quantum algorithm. So you can think of this as a subroutine. And we're actually going to be using the inverse quantum Fourier transform. So we're going to go from the Fourier basis, and we're going to map back to the computational basis. So how do we implement the inverse of a unitary operation? Well, because this is unitary, this quantum circuit is actually reversible. So if we start from the right over here and we move over to the left, it's the same as turning back time. So by convention, time is going from left to right. And if we read the diagram in reverse, that is the inverse. So it's the inverse quantum Fourier transform. And we're going to use that to implement the phase estimation procedure. So now let's examine this diagram in the bottom over here. This is going to give us an intuitive understanding of quantum phase estimation. So we're going to consider a specific scenario involving some unitary operator, which I've called U. So this unitary operator has an eigenstate, which I'm going to label by lambda. Lambda is the label for this eigenstate. And the eigenvalue associated with this eigenstate is e to the 2 pi I, and we're going to have phi up here. So phi is part of this phase factor. And this eigenvalue multiplies the eigenstate, lambda, when U acts on it. So this is an eigenvalue equation. And what we want to do is estimate this phi. So we have knowledge of this unitary operator, and we also know that this is its eigenstate, but we don't know what phi is. We want to figure out what phi is. And this is the scenario that we're going to use phase estimation for. So phase estimation is going to actually allow us to estimate phi. Let's consider what phi is. We can represent phi as 0.phi1, phi2, ... all the way up to phi sub n. So this is an n-bit representation of phi. And this is not normal decimal notation. What we're actually dealing with here is binary. So alternatively, we could write this as phi is equal to the sum of some index j going from 1 up to little n. And here we're going to have phi sub j. That's each of these bits over here. So this is a string of zeros and ones. And then we're going to have 2 to the minus j. So this value, that's one behind this point over here. So this is just like a decimal point, but we're dealing with binary. This is the 1/2 place. And then this 2, this is the 1/4 place. And then over here, what we're dealing with is 2 to the minus n. That's this last place over here. So that's when j is equal to n. We have 2 to the minus n. So this is our representation for phi. And when we put this phi inside here, we're not interested in any integer multiples. So that's why we start with 0. Because an integer multiple of 2 pi, when we put it inside the complex exponential, that's going to correspond to a full revolution around the unit circle in the complex plane. And that has no effect. It's equivalent to multiplying by 1. So that's why we're only interested in values after this point over here. So that's an explanation of what phi is, and we're also stating the problem. Now let's see how we can use the inverse quantum Fourier transform to extract information about this phi, given that we have knowledge about u. Consider this quantum circuit diagram over here. We have 2 registers. We have a top register with n qubits, and then we have a bottom register with capital L qubits. So this line over here tells us that we're not dealing with 1 qubit, we're dealing with L qubits. So this is a condensed notation over here. So in this entire bottom part, you can imagine many lines over here. So it's however many lines we need to specify the state denoted by lambda. And that's that eigenstate of the unitary operator. We will begin by applying Hadamard's to all of these qubits after they've been initialized in the state 0. So first we initialize in this computational basis state. So it's all zeros. All of the qubits are initialized into this state 0, and we have n of them. Then we apply the Hadamard gate to each of them, and that prepares a superposition of all the computational basis states. Once we've done that, we're going to apply these controlled unitary gates. And we're going to start off with u to the 2 to the power of 0. 2 to the power of 0, that's equal to 1. So here we're just applying the controlled u gate. Then we're going to apply the controlled u squared gate. And we're going to keep going with this pattern until we get to u to the power of 2 to the n minus 1. So 1 less than 2 to the n. So we have 1 less power. That's because we start at 0. But in total we have n of these gates. If we include 0, that's our first one, and then we go up to n minus 1. Now, notice that there's a lot of dots, right? Just like in this diagram, we have omitted a lot of details because this is a general diagram that works for n bits or n qubits. So that means we have to omit these guys. So we can see the first qubit, and we can also see the second last qubit and the last qubit in this first register. And all of these intermediate stages where we're going to be applying many controlled unitary gates, those are omitted. But you can see the pattern and you can imagine what these controlled unitary gates would look like. They would satisfy this pattern, but they would be intermediate values for this exponent. And what happens when we get to the very end? Well, this bottom register still is in this eigenstate. So for now, let's ignore what's happening to this bottom register. So we're no longer interested in this bottom register. Now we're just interested to what's happened to all of these states in the top register. So they began as initialized in the state 0, and they have progressively been turned into these superpositions of 0 and 1 with phase factors. And we also have normalization coefficients. So the Hadamard gate would just produce a superposition of 0 and 1. And this phase factor would just be 1 over here. And these controlled unitary gates have, they're responsible for these phase factors. And you can see that inside each of these phase factors, we have the power of 2 that corresponds to this power of 2 that occurs in each of these controlled unitary gates. Every time we apply u to an eigenstate, we get this eigenvalue. So we have one factor of phi. And if we apply this controlled unitary gate multiple times, or if we have u to the power of some positive integer, that's going to correspond to 2 to that power inside this exponent. So that explains where 2 to the 0, 2 to the 1, and 2 to the n-1 are coming from. And then these dots represent all of the intermediate values. Now let's take this general state over here and take the tensor product of all of those terms. And let's see what we can actually extract, what kind of information we can get from that. So the normalization coefficient can be grouped together into one normalization coefficient that is equal to 2 to the minus n on 2. So that's what happens when we take all of those factors of 1 on the square root of 2 and we smush them into one normalization coefficient out the front. Now let's consider what this is equivalent to. We're going to have 0 plus this coefficient. And let's examine, based off of this, this binary point over here, this notation in binary, let's examine what's happening to this value of phi. So we are multiplying by 2 to the power of n minus 1. That corresponds to a shift. If we look at this definition, it's the same as a shift by n minus 1 units. So what does that actually mean? That means that we're going to shift this point all the way to in front of this n. And what is that going to do? It's going to take all of these values and it's going to turn them into integers that are greater than the decimal point. So that means they are 1 and above. And so they are positive integers, and they are going to go into this complex exponential, and we're going to have positive integer multiples of 2 pi. So that's equivalent to going around the circle. And if we keep going around to the circle, we're going to come back to exactly the same spot. And that's the same as multiplying by 1. So we're only interested in what is remaining on the right of this point. We're not interested in all those other values. So the value we're going to get is e to the 2 pi I times 0.phi n. So that's the only one that's going to remain. We're not interested in the other terms, phi 1 all the way up to phi n minus 1, because they are a positive integer that's multiplying 2 pi. And that's the same as multiplying by 1. So this is going to be the first term. This coefficient over here, this phase factor, is equivalent to this phase factor over here. And now we're going to take the tensor product all the way up to the last two terms. So I'm going to put some dots over here to show that we have all of the intermediate terms. So that's the first one, and now let's consider the last 2 qubits. So the last 2 qubits are going to look like this. We're going to have e to the 2 pi I, and what is this shift? This is just a shift by 1 unit. So we had a shift of n minus 1 units, and now we're going to do a shift of 1 unit. And that 1 unit is going to get rid of this. So this is going to go in the left-hand side of this point, and it's going to turn into an integer. So we're going to have 0.phi2 all the way up to phi n. So that's 0.phi2 ... all the way up to phi n. And this multiplies 1 over here. And now let's have a look at the final state. The final state is going to have the form 0 plus e to the 2 pi I. And what is this shift over here? We have 2 to the 0. We're shifting by 0 units. That means we're just going to have this form over here. We're not going to change it at all. So that's going to be 0.phi1 ... all the way up to phi n. And this is the phase factor that we have over here. So what we've actually got is the result of applying the quantum Fourier transform. So we can apply the inverse quantum Fourier transform to extract the original state. And let's write this in a similar form. So we'll write this in an equivalent form. We can have the same normalization coefficient over here. That's 2 to the little n on 2 with a minus sign over here. And then we can write this in summation notation with some index k going from 0 up to 2 to the n minus 1. And all of these phase factors, we can write them as one phase factor. That's e to the 2 pi I times this index k multiplying phi. So this is a condensed way of writing all of those phase factors, and this is going to multiply the state k. So these are two different forms for the result of applying the quantum Fourier transform. And what did we actually apply the quantum Fourier transform to? What was the original state? Well, we can extract it from here. I'm going to write it underneath. So this state over here was actually the state phi 1, phi 2, ... all the way up to phi n minus 1, and then phi n. So if we prepared an initial state in this form, where these are zeros and ones, we have a bit string, then if we applied the quantum Fourier transform to this, we would get this big expression over here. So to go from here to over here, we apply the quantum Fourier transform, and then to go the other way, we apply the inverse. And I can write that using this notation. So if we go this way and this way, there's two different ways we can do this. So for this way, we are applying the quantum Fourier transform, which we can denote as f2 to the n. So it's the n-qubit quantum Fourier transform. And over here we have f2 to the n with an inverse. So this is the adjoint, the Hermitian adjoint. And a very important property of the quantum Fourier transform is that it is unitary. So we can write that as f for an n-bit system or an n-qubit system times f 2 to the n inverse, or the Hermitian adjoint, that is equal to the identity. And we can also swap the order around. We can write the inverse first, and then we can apply the quantum Fourier transform. And either way, the quantum Fourier transform is going to undo the action of its inverse. And we're going to get the identity. So it's the same as not doing anything at all. And you can see that you can start off in this state, apply the quantum Fourier transform, and that gets you to this state. And if you begin in this state, which is what we have in this phase estimation circuit, then we can apply the inverse quantum Fourier transform, and it will extract this information out of these states. And what is the information in here? Well, this is a computational basis state, so we can measure the first register, and that's going to give us a string of bits that correspond to this estimate, an estimate for phi. So we are extracting information about phi from this state, and that state is has been achieved by applying the inverse quantum Fourier transform. So you can see that this is very useful. We have a phase estimation procedure. Now, in this example, I have specifically picked a value of phi that can be expressed as n bits. So we have an n-bit representation of phi, and that allows us to get this specific computational basis state. But in general, you might not be able to express phi in n bits. So if you can't express it in n bits, this is just going to be an approximation. That's why this is called phase estimation. It might not be the exact value of the phase, but it is an estimate. And the more bits you include in this first register, the better the estimate is going to be. So we can actually complete this phase estimation procedure by adding the inverse quantum Fourier transform over here, applied to the first register. So we take all of these qubits and we feed them into the inverse quantum Fourier transform, and then we measure all of the qubits in the first register. And from that, we extract this information about phi. We're going to be using this procedure to implement the order finding subroutine of Shor's factoring algorithm. So that's going to be the next video.